That's only a theory. So, hey, welcome everybody to Astronomy Daily Live. It's 2 hours UTC, and it's time again to gather together this worldwide group of great friends and come together and chit chat for the next, I don't know, little bit, hourish or so about all things astronomy and space and science and nerdy things, that kind of stuff. So yeah, hope everybody's doing well. It's the sun is setting here in Arizona, and
poor Carolina.
all is well. What is going on with Carolina?
It's cloudy again, and that depresses him.
Yes, absolutely.
Holy canola.
Yeah, that's how it goes. I don't know if everyone's noticed yet in the chat, but the emojis have changed. So at least what I'm seeing, they have changed. So no, maybe not.
I don't know. I don't see anything new. What do you see that's new?
If I do a thumbs up.
I don't see any changes on the app version. It's probably on my Google Chrome and stuff.
Maybe it's just me, but the emojis here. Let me share my screen. I'll show you what I'm seeing. And this is sort of a prelude to getting into all of this. So I haven't said hi to anybody yet, but I just want to show. I'll just show this off since it's here, because this is what I'm seeing at least. If I go over to the chat, you can sort of see. Look at these. They are different, right? And if I do like a smile, look at that. So is that just me or is it just you? Anyway.
I got it on Chrome and stuff like that. But on the YouTube app, it's all right. So, hello everyone. Bobby Burgess, Morgan City.
Bobby's here.
Atta, the lovely, sexy, talented trekker. Atta. And shows up for Earth Radio.
Earth Radio. And Atta, there you go. You're on cue.
Johnny, Helen, they ran away through the haunted house. The floor creaked, groaned with every step. Who was that ghost? Slowly fluttering around them. In a flash, they saw gray shapes float through the air. Traveling through the wall.
I need one of those.
Solid objects.
I need that.
There. Got away from the ghost. Was the one door not blocked by restless spirits. Door to the basement. Helen threw open the door. And what did she see standing there? Tune in to next week's broadcast to find out.
I like that.
I finally found your channel, Ert. I'm not much of a radio person, but, I found your channel. I just thought I'd let you know.
And there's Chuck, Jim from Carolina Sky, Tom, Ron from Earth.
So did you really find my channel?
I did.
Okay.
All right, well, cool. Well,
now, YouTube or Mixware?
Yeah. All right, well, cool. Well, welcome, everybody. We've got some new toys here that Atta likes to show off, and that one actually we first saw on FranLab, and she got it as some kind of package from a fan, and Atta liked it so much that she figured out where to get it, and she did. So pretty good there.
Yeah, I froze Fran's video, at least a frame of it, and blew it up so I could try to see some designation on here.
I'm pretty good.
Pretty good. Pretty good.
It is.
All right. Well, hope everybody's doing well out there. It's this is the 2nd of July, 2019. What is it? 2:06 UTC. So yeah, in a matter of like 16 hours or so is the solar eclipse that's going to be going sort of, right across the south Pacific and hitting South America, Chile, and Argentina. And there's a lot of excitement down there, lots of traveling, a lot of, final things because they've got a mere 16 hours left.
A lot of people travel all over the world to follow, solar eclipse.
Oh yeah. No, I mean, that's a way to sort of have a destination every year. And you just go and you see your solar eclipses. They are extremely addictive. Once you see one, you sort of really want to see them all, right? So
yeah, you can see why primitive people really got freaked out when that happened. They thought the world was coming to an end and all that stuff.
No, it's I've never been in a total eclipse. I've been in well, the closest I've been to is where the sun makes a ring of fire around the moon.
Oh yeah.
That was extremely impressive. And
there is Stage Master probably teaching some students at the Montgomery Scott School of Engineering at Starfleet Academy.
Nice. So he's just taking a break, I guess. So, and Atta's got the See, Atta's a time traveler. I don't know if I was supposed to. I don't know if I was supposed to mention that or not, but I guess it slipped out. So
I get around.
She gets around.
Absolutely.
For sure. All right. Well, cool. So, I thought what we could do today is at least a couple of things. One of the things that I don't know if I've done this on this live stream or not, but we're going to do it now anyway. It's a little bit of some not really mathematics, but we're going to take a very, very famous equation and make some computations. One of the interesting things that I heard long ago, and when I heard it, it was just like that. No. And what I heard was this: is that the force, the gravitational force that the moon feels from the sun is twice as strong as what it feels from the Earth. The sun is pulling on the moon twice as hard as what the Earth is pulling on the moon. And I thought about that, and it's like, what? That doesn't make any sense.
Yeah, it doesn't make
that doesn't make any sense because we
wouldn't it be the same force basically?
Well, if the moon is orbiting the Earth, it would sort of seem logical that the force that the moon feels would be strongest from the Earth, and the sun, would play a little bit of a role, but not all that much. So I thought about this, and it's like, well, there's only one way to prove this, one way or another, and that is to go to the famous gravitational equation of Newton and plug in some numbers and see what the forces are.
Ida was crying on that one.
I got a feeling this is war. This is definitely war.
Is it the fact that the reason why that the moon is moving away from the Earth?
I think that might have something to do with it. So what I want to do is look at the numbers and actually see if that's the case. And if it is, it's like, okay, well, that sort of changed my view of the relationship between the Earth and the Moon. And I've heard this many times now. It's well, it's sort of a perspective thing, but it's sort of like the Earth and the Moon are sort of co-orbiting the sun. They just so happen to be sort of next to one another, and so they do this. And from our point of view, from Earth's point of view, it looks like the moon is going around, but in fact, what they're doing is sort of a weaving thing as they go around the sun. Yeah, I mean, it's a matter of perspective, right? From the sun, it looks like one thing. From the Earth, it looks like a different thing. From the moon, it looks like a different thing.
That Tom is saying that's due to the tidal interaction between the Earth and the moon.
What is
I'm going
a
little further. Yeah, okay. I'm going a little farther back than what you're talking about. I believe in creation of the universe. Not that we're getting religious or anything like that, but just as an example, I believe in the creation of everything, and it was placed, and then it's revolving around whatever is going around. Where some deviate from that point of view is that the moon came from planet Earth, somehow got chipped off of the planet, and it wound up as being part of the moon system. Which I don't know about that. I don't know if there's any proof on that. But as far as the creation thought of it, they were both created at the same time. However the Bible describes it. Not that I'm trying to push that or anything like that, but just trying to give an idea.
Yeah, that's cool. And my opinion is that the best story wins.
It's the fact that the moon is moving away from the Earth. If you would check the chat.
Okay, I got you. Yeah. My thought is that the best story wins. So, all right. So, what I want to do is a little bit of math. This live stream is.
You got a calculator?
You know what? I've got something even better. We're going to use a spreadsheet. We're going to use a spreadsheet. Yes,
right on the Rebray office. That's baby.
So this live stream is about numbers. Not trying to simplify things, because I don't think anybody here is simple, right, or not very intelligent or anything. So let's keep it at a high level, and do what actually is some pretty basic math, but there are some complications, and I will get into that once we start. So what I'm going to do is I'm going to make sure that I'm ready to go here. Yeah. Okay. I'm going to share my screen. And here we go. Well, math is a tool, and it seems to be applicable everywhere. Whether it is or not, it's hard to tell. But it's like a hammer or a screwdriver. It's just a tool. It's not the thing itself. Anyway, this is the famous equation that we are going to use. And what this is saying is that the gravitational force that is felt between two bodies that have one mass, the mass of one of them and the mass of another one, is this kind of relationship. So there's this thing called big G, the gravitational constant, which is well, it's kind of an interesting number. We'll look at that in a minute. So it's that number times the mass of the first body times the mass of the second body divided by the distance between them squared. And that's it. That's all it is. Now,
yeah, but in the case of the Earth and Sun, the mass of the Sun would be so much greater than the Earth.
Right.
M2 would be negligible practically.
Right. But
we're going to say goodbye to Pagemaster as he's going to be doing some more awesomations with his new scope.
All right.
Good. Thank you.
Good for you.
All right, Pagemaster.
Thanks for coming in. We hope to hear a great report. Great report. So have a ball. Have a good time out there, Pagemaster. Okay, so there are sort of two steps or two different things that we have to look at when we look at these kinds of equations. We actually have to look at the numbers, right? We have to plug in all the numbers and da-da-da-da. But, you know,
I can only dream of that.
But, you know, the other thing that we really have to pay attention to are the units, okay? Yeah. So, of course, mass is going to be in, you know, like kilograms or grams or something like that. We're going to stick to metric here. It doesn't really matter what the units are, you know, the numbers are, just as long as we're consistent, right? So we can't have mass 1 being in grams and mass 2 being in kilograms, say. You know, they all have to be the same.
We got that, Cosmic.
Good. We got that. Excellent. All right, so let's look at the gravitational constant, and you will see some pretty weird units. It's in
the same formula basically from start to finish with the equation.
Well, this is just the value of G.
Meaning the same formula, like you said, don't switch up the or style or whatever. You have to have the same principle that you're working with all the way through. Correct.
So as you can see, the units for G are in cubic meters per kilogram per second squared. That's a really, really weird unit. But that is what it is.
Okay, what is the F? What is the force? Okay.
That's the force.
Okay. I got it.
That's the force that is being felt, you know, the gravitational force.
Okay, so what is the R? The R is the total radius of...
R is the distance between the two masses.
Okay.
Okay, so that's what that is. Yeah, in fact, here's the equation here again. Okay. So G has these weird units of meter.
That's weird.
Very, very weird. Meter cubed per kilogram per second squared.
Per second.
Yeah. A little bit weird. So I think
what is the F for again? The F is what?
The F is the gravitational force that is felt.
Force. Okay, force. Okay.
Yeah. So I think what we should do, let's do, what's the best way to do this? I think what I want to do is, let's see if I can do this.
Okay, m squared is the mass.
No, that's not it.
Times, or mass times itself twice. No, I don't know.
Yeah, there are two masses. Yeah,
not m squared. It's m2.
Yeah.
M1 and M2. Mass of the first body, mass of the second body.
Okay.
R is the distance between the bodies.
Okay.
Yeah. Exactly. Let me I need to, because I want to work out these units before we really dive into it too much. I'm trying to figure out.
Gee, if I'd have known you were going to do this, I'd have brought one of the kids I tutor over.
Well, this is
that equation.
nice. Let's see. How should I do this? I'm going to do this. I'm going to go stop sharing. Let me pull up one more screen that I really need in order to get this, so it's a little bit easier to show off. Let me find what I'm looking for here. Looking for
a couple more screens over there.
The object of your exercises is trying to prove that force that you read about it being twice as strong on.
I just sort of want to see if that's the case or not.
Yeah.
Okay, so I've got my little drawing thing up here. So let me do that again. Do like that.
But that would do one of two things. That would either, like what Bobby was saying, would pull the moon away from, or what Tom was talking about, that would pull the moon away from the Earth.
Mm-hmm.
Okay. And or it would split the moon in half.
Right.
If the force was any greater on either side, the moon or either on the Earth side or on the sun side, either one, it would split the moon in half. And obviously that's not happening.
It's not happening.
So that means that there's some kind of force there's an equality of force between the sun and the moon. There's a center, you know what I'm saying? Like when you have two stars that are orbiting each other, there's a gravitational center, right?
Correct. That's right. Uh-huh.
So in our situation with the moon, even though the moon is a smaller body, and of course the sun is way bigger than the Earth as far as the power is concerned, you're looking at, well, you'd think that, you know, the moon would either be pulled off track or it would be split apart.
Uh-huh.
Those are the only two options you have, unless you found a center point where the moon was, like in that Goldilocks zone, so to speak.
Okay.
And then, therefore, it stayed together, and it also stays in orbit.
Yeah, that's why, the explanation that I've sort of come on is that the moon is going around the sun pretty much just like the Earth is going around the sun.
Mm-hmm.
And so, the forces are just, there's a balance there, and it works out. But
Tom is saying that the sun side changes constantly.
Okay. Anyway, let's work through these units first, and then we can plug in all the numbers and see what happens.
Yeah.
So G is going to have these units. So cubic meters. Here, let's see if I can. I'm not going to be able to draw this really well, but I'm going to try anyway.
I thought you were going to use a spreadsheet, not paint.
Yeah, I am, but we got to do all the units first. Definitely. So
then for those sizes of those objects, you'd have the diameter of the Earth, right?
You don't need the diameter of the Earth. You just need the mass. But you're jumping ahead a little bit. Let's not move too fast.
No, we just look at a diagram here.
Yeah. So the mass of one is going to be in kilograms, because those are our units of G here. The mass of 2 is also going to be in kilograms. So that's actually kilograms squared, right? Mass 1 times mass 2 is actually going to be in kilograms squared. So I cannot do this very well. It's very painful and very ugly looking, but that's all right. So kilograms squared. Okay. That's why I'm not an artist. And then R is going to be in meters, right? But it's R squared, so we're actually going to do meters squared, right? So we're squaring all the units. So that is divided by meters squared. So we're going to divide by meters squared. Sorry about the horrible drawing here. I'm going to have to do something much better than that.
You're doing.
That's the worst 2 ever. Okay.
That's how I do my 2s.
Oh yeah. Well, that's how I do my 2s on this thing, at least. Oh, so we forgot these parts: the kilogram per kilogram per second squared. We have to add that to this thing. So we're going to do that. This is getting a little more complicated than what I thought.
So
how am I going to get
this was that the force between the sun and the moon is 2 times the force of the Earth to the moon.
Yeah, let's just I'm
not putting in any real numbers. I'm just working with the symbols to see what I get here.
Well, the symbols should all just sort of work out. I think I should have planned this a little bit better. Let's not worry about the units. Let's just plug in some numbers. Okay. So first thing to do really is to go over to the spreadsheet and get this equation going. So let's get our number for big G. Okay. So we're going to go over here and we're going to grab it. I'm just going to erase this whole horrible thing here.
Just share the app.
And so G is going to be this number. It's 6.6743 times 10 to the minus 11th. Okay, so I'm going to grab that and we'll copy and paste over here. I think, let's see. Can I, where are you?
So that's the blue dot or blue circular is mass 1. Okay.
Correct. Well, I'm just going to type it in then because it's just not wanting to do that. So 6.6743 times 10 to the minus 11.
Oh boy.
6.6743 negative 11, like that. Okay, that's G. Spread that out so we can see the whole thing.
But is that suspicion correct though? If it did not find the center zone of the orbit, then it would be pulled apart.
It would definitely probably experience tidal forces. Yes.
Okay.
Pulling apart sort of depends on the structure of the object itself too. So that's a little, I'm not
all right.
Quite sure about that. Okay. So we need a mass of 1 and a mass of 2. So let's call M1 the mass of the sun. So let's go look up the mass of the sun in kilograms.
It's going to be a big number. It's going to be a big number.
Yeah, pretty big number. Let's see here. Mass. Here we go. So 1.9885 times 10 to the 30th kilograms.
This is where your intern Bobby should be getting all those answers for you. You should already have them.
There you go. All right, so 1.9885. 1.9885. So we'll call this the mass of the sun. We'll just call it MS like that.
Yeah, right. Truth to be told, it's been a long, long time since I fiddle faddled with spreadsheets.
Let's go. Since we're here and I saw it, there
I was just picking on you, Bobby.
There is an average distance or a mean distance between the Earth and the Sun. So that's our R here, which we're going to square eventually. But so that's 1.496 times 10 to the 8th kilometers. Now, is that the right unit? No, we want meters.
So in most equations, you always have constants, correct?
No. I mean, it completely depends on what's being done. In this particular case, there does so happen to be a constant, but that's no.
Well,
that's
like you have, like for instance, you always have, almost every math equation I've seen, you always have a base or a root that you can start from. So, for instance, you got 2 plus 2 equals 4. You know that. Okay. You have to have a 2 in order for it to equal 4. You have to have the first 2 in order to get the second. You know what I mean? You have to have part of the equation in order to get it.
That sounds very.
Good to be told, the number 2 is the onlyest prime number in our prime number system.
That is totally untrue. The number 2 is the only even prime number there is.
Okay.
Yeah, that's what I meant to say.
But okay, what I was going to say though is if you have for our equation here though, we need to know the mass of the object, which would be the Earth, and the mass of the sun. Mm-hmm. And we don't have to know the mass of the moon?
Yep, we're getting there.
Okay, I'm just making sure we need to know all 3 sizes, and that would be your constant for the equation.
Well,
that's what I'm saying.
Yeah. Everything in this equation is a variable except for G.
Oh.
Everything else, you can plug in anything you want.
Yeah. I think the truth about prime numbers is if you're going to have a solution only one time, then it's considered a prime number. If you have it more than 2 or more times, then it's not a prime number.
That's a good way to look at it. Mm-hmm.
So what's a prime number then?
It's any number that is only divisible by itself in 1. That's it. No factors. All right, so let's keep going here. So we've got the gravitational constant. We have the mass of the sun. We have the distance between the Earth and the sun. Let's see. We need the mass of the Earth, and then we can do at least our first one. So let's get the mass of the Earth here. Let's see, we'll go back over here and we will search for Earth. Where is Earth? Here we go. Probably going to be a little less massive than the sun. A little. Here we go. Well, it's only 1,000,000 times less massive. So this is in kilograms. This is kilograms, so we're good there. So what is it? 5.972 times 10 to the 24th, 5972. Mass of the Earth, 5.972 times 10 to the 24th, all right? Okay. So with these four numbers, we can actually compute the force between the Earth and the Sun. We'll just call it FES, like that. And that is just going to be G. And in fact, we'll do it like this, so it's really clear. Yeah, so we'll do G times mass of the Sun times the mass of the Earth divided by the distance between them squared. Can I do a squared like that? I think I can. Whoop. Uh-oh. Let's try that again, sorry.
What the heck did you just do?
Oh, who knows? Crazy astronomer at work here. Divided by the distance. I think we can do squared like that. Yeah. So this is going to be in units of, I believe, in units of newtons, but totally. But let's not worry about the units too much. Let's do one more. Let's get the mass. We actually need two more numbers to compute the force between the Earth and the Moon. We need the mass of the Moon, and we need the distance between the Earth and the Moon. So let's do that. I'm going to move this down, I think. Let's just move this down. We'll just move it way down here. Like that. Okay. So let's do the mass of the Moon. Let's get that. And that's going to be even smaller than the mass of the Earth, we hope.
You're making very sure you keep the same units, right?
I'm trying.
Because if you don't, that's screw the whole thing.
Yeah. Yeah, no, we're in MKS here, right? Meters, kilograms, seconds. So we're good there.
Because you're just looking for a relative comparison.
Yeah.
So
yeah.
It doesn't matter what you choose as long as it's the same for both.
Well, as long as the units are the same, we are golden. Yep. Okay, so this is in kilograms, so we're safe there. So 7.342 times 10 to the 22nd.
You said gold?
7.342. Yes, I did. 7.342 E22, did I say? And that memory of mine is just shot. Yeah. Okay. And we want sort of the average or mean distance between the Earth and the Moon. We've got an apogee and a perigee. We can do that. We can do a semi-major axis. That's almost the same thing. Nope, that is the actual radius. So why don't we just take the average of the perigee and the apogee? So I'm going to grab my little calculator here. 362, 600. Now notice that this is in kilometers. Okay, we don't want kilometers, we want meters. So we're going to have to multiply everything by 1,000 in order to get that. So you definitely have to remember that. So 362, 600 plus 405, 400 divided by 2 is 384,000 kilometers. So it's actually going to be 384 million meters. So we can go over here, and the distance between the Earth and the Moon, let's just call it, since we called this the distance to the Sun, let's call this the distance to the Moon. And we're going to call it 384 million meters, like that. Okay, and I think that's all we need. So the force between the Earth and the Moon is going to be the same equation. So it's G times the mass of the Earth times the mass of the Moon divided by the distance between them squared. Bam. That. Wow. Huh. Now, I'm wondering if I've got my units messed up somewhere, because this is a factor of about 200, not a factor of 2. You see, this is 2 exponents here. So let's let's go back and make absolute certain that I did all this right. This, this is part of what astronomers do and scientists do. Look at these things. It's like, that doesn't seem right. And you got to go back, and it's tedious and it's painful, but that's just how it goes. So let's check our work. Is that there's something not quite right there. Let's see where I might have messed up. You count on me to mess things up as long as I do it really well. So the mean distance is in kilometers here, so I have to multiply that by 1,000 as well. So that should be 1.496 times 10 to the 11th. Is that what I'm doing here? The distance between the Earth and the Sun? Yeah. 10 to the 11th. Yeah, got that right. Mass of the Sun. Where are we here? This is part of it, at least. This. Oh, no. Kilograms. That's right. Kilograms is what we want. Yeah. So that's 1.9885 times 10 to the 30th kilograms. All right. Let's fix all these so we can see all the decimal points here. Oh, what did I do? And number of 4 decimal places.
What the hell you just did?
I don't know what I just did. A little weird. Let's all right. Well, maybe I won't. So the mass of the Sun is right. The distance between the Earth and the Sun is correct. Let's look at the mass of the Earth. Maybe I misplaced that one. I don't think I did, but well, we'll find out. Earth. Pretty nice place. So let's look at the mass here. So this is in kilograms again. Those are the right units. 5.972 times 10 to the 24th. Is that what I've got? Yeah, that's what I've got. I've got those units, right?
Yeah, today they had me playing some real oldies today.
Oh, good.
Oh, yeah. My friend Dick, he had me looking up or playing from 1926. Holy cow!
Wow, nice. What do you think about the news about the UMG fire that happened back in 2008? Did you hear about that?
Yeah, and Bobby was telling me a little bit about it. Yeah.
That is some of the worst news I've heard in a very, very, very long time. It was bad news.
Yeah.
7.342 times 10 to the 22nd kilograms. 10 to the 22nd. I've got that right.
There ain't much you can do about that, I mean, things happen.
Yeah, well, there's just it's like losing the Mona Lisa,
Right.
or losing any of those things, and not telling anybody that it happened.
Right.
So 362 600 plus 405 400 divided by 2. And then I'm going to multiply that by 1,000 again. So that's 384 million. And that's exactly what I've got there. So, what am I doing wrong? 384 million. B3. Okay, so B1, B2, B4 divided by B3 squared. And this one is, those two equations sort of look different. Let's make them look exactly the same. That doesn't make any difference at all. I didn't think it would. B1, B4, B6, and B7.
Maybe I can welcome Deep Sky Dude in the chat.
Hey there, Deep Sky Dude.
Are you still streaming from the Star Party or what?
He put out a video today of the Star Party. It was great. I wasn't able to see all of it. I came in late.
Messing up the equation there. He's messing it up real good.
Yeah, I'm a little perplexed about this, because this is showing that the force between the Earth and the Sun, here we can actually
now remember, you had an average of the
divide those two.
You had the average of the radius, right? You had the average of their distance. The moon.
Yeah, but that doesn't
make any difference. That
wouldn't make a difference. Okay.
Not a lot.
No,
not really a lot. No, but
not
we're
200 times.
Yeah.
Well, I was just wondering.
Oh, sure. Yeah. No. Check my work here, because there's something a little funny here, because we're seeing almost 200 times. And
get the torch. Get the torch.
There's something wrong about that. There really is. So I thought it was a couple times, not 200 times. Meter, kilogram per second.
Maybe you screwed your D wrong.
No, it's right there. Times 10 to the negative 11th. That's what I've got. Mass of the Sun. I think all that's right.
Yeah.
So
weird.
Okay. Well, probably what's going to happen is I'm going to end the live stream, and then I'm going to look at this and I'm going to say, "Oh, of course, you dummy. It's just this, and this." But
the fact that it's still, though, around 2-something, 200, 2,000, 2 million. 2 is sort of the magic number there. Right?
Yeah.
But to think.
Well,
that's
this
correct.
number is very, very close to 200. So that's why. But yeah, I think we're off by a factor of 100, though, and I'm not exactly sure why. I think I'm doing all the math right. Multiplying and dividing is commutative, so maybe.
Now, when you're looking at that exact equation, though, you're only looking at the 3 bodies in question: the Sun, Moon, and the Earth, right? You're not talking about everything else involved with the solar system.
Yes, this is a very, very, very simplified model in that case. It works it works amazingly well, though.
When you have the right number.
When apparently you have the right numbers, but this is what I'm getting. So
functionality is there, just not the right answer. Yeah.
Well, I'm not quite sure what the right answer is anymore, because everything that we're doing here is correct. Well, fact of the matter is that these forces are different, and I think it's still relatively safe to say that the force that the oh no, wait a minute, I know what's going on. I know exactly what's going on. Duh. We don't want, okay, what we want to know is the gravitational force between the Earth and the Moon and the Sun and the Moon, not the Earth and the Sun and the Earth and the Moon. Mm-hmm. This one's right. This one isn't. We want the Sun, and the
Moon. Yeah.
That's not the Sun and the Earth. Yeah.
Right.
So, duh. So it's all we have to do is, instead of plugging in the mass of the Earth here, we plug in the mass of the Moon. So that is that is B6. So let's, instead of B4, let's do B6 right here. That's what it is. Bam. There we go.
Now we are getting somewhere.
Yeah. Now you see, one is almost twice the other.
Yep. Let's go F.
A little over.
Yes.
I say, boy, now you're getting somewhere.
Yeah, thank you. You've just seen a perfect example of how dense cosmic can be, right?
We're glad you didn't have to wait till tomorrow to tell us.
It's just incredibly insane. Anyway, so here is the gravitational force that the Moon is feeling from the Sun, and here is the force that the Moon is feeling from the Earth, and this divided by this is this number.
Yeah.
And it's just a little bit more than 2. So
close enough to 2 to prove it. I mean,
yeah. So the Sun is pulling on the Moon twice as hard as the Earth is pulling on the Moon. So why does the Moon even stick around, right?
Right.
And that's an interesting question to contemplate. If it's feeling twice the force, why does it stay here? Well, it probably has to do with the fact that it is relatively close to the Earth, and so the Earth is playing a role in the Moon's motion. Anyway, it's just an interesting thing to think about, and it's sort of non-intuitive. You would think that because the Moon is so close to the Earth, that the force in between those two bodies would be more than the force between the Sun and the Moon. The Sun is so far away, but it's just so much more massive. There's just so much more stuff there that it works out just like that. So
remember,
kind of interesting.
There's another force in there involved too, and that's the force between the Sun and the Earth. You're not just balancing the Earth and the Moon and the.
So I still have the problem of it not being balanced. If what you're saying,
you've got 3 forces interacting,
and there's something that's not being balanced here, and in reality, if what you're saying is the case, then the Moon would have been gone a long time ago.
Yeah, it gets complicated really, really, really fast. But it's just an interesting, perspective. It's non-intuitive and yeah, it's a little confusing. So yeah, there's some interesting things to think about. The math says that the force is about twice as much, and yeah, I think that's about right. Those I think those kinds of measurements can actually sort of be made, and that's exactly what they come up with, too. So pretty interesting stuff. Non-intuitive, doesn't make much sense unless you sort of consider the fact that the moon isn't necessarily going around the Earth. It's sort of going around the sun with the Earth instead.
Yes, that's exactly right.
Thanks, Tom.
Force operating between the sun and the Earth as well.
Yeah.
Right.
There's a third force there.
Okay.
Think about.
Tom got
All
a bit
right.
of history.
All right, so
What's
on
that?
this day in 1917, the 100-inch mirror for the Hooker telescope was delivered to the Mount Wilson Observatory. It was the largest aperture telescope in the world from 1917
Until 40.
until 1949.
Wow.
Nice.
And
Yeah.
Arthur, what year you was born in?
Get out. Get out.
Those kinds of questions are not necessarily allowed. You will be penalized.
You're stuck with you?
Yeah, I think in 1949, that's about when Palomar, the Hale telescope, the 200-inch telescope, came online. Was somewhere I think in the 50s or something like that. I forget exactly. But yeah, you have the 100-inch telescope. I'm pretty sure is still being used today. Wow, that's 102 years ago that came
That in
online.
my living room, I think.
That's older than I am, Bobby.
A little bit.
Oh, I can't remember that.
Yeah, and in fact, over on my Discord server, I think I put it over there. I just posted a picture of the construction of the the large synoptic survey telescope, and they actually have sort of looks like the structure of the dome is going up right now. So very, very cool. That's I think that's another. I think that's about an 8-meter mirror, I think, or something like that. It's a pretty big one. It was made.
Take.
What's that?
My computer's transgressing.
Oh.
Your computer is transgressing.
See what happened? See what happened? You got smart.
Yeah, that's exactly what happened. So, all right, well, cool. I think I'm looking at the time, and it's really, really, really close to 3 hours UTC. So I think I'm going to end this live stream a little, almost on time, I guess, which is extremely rare, and pick things up again tomorrow.
All right.
Tomorrow, more astronomy. Tomorrow, I want to map more of that asteroid as well.
What I want you to do for homework for tonight. All right, and then I want the whole equation done for tomorrow night. I want the whole solar system mapped out with your equation. Just kidding.
Well, now that we have a spreadsheet, simple. Simplicity itself.
All
so
right.
no problem at all. But yeah, it's kind of interesting. What we should probably do is actually look at what some other moons and planets are doing. You know, we can take
like Mars, like the Martian system,
either the Martian system or the Jupiter system or Saturn or anything, and see what the forces there are. And my guess is that they are going to feel a huge force from their planet and a pretty small force from the sun, because the distance is a lot more. Don't know though, but maybe we'll look at that again.
Interesting. Huh?
Yeah, it's pretty interesting, for sure. And it's sort of the first stage in getting into, you know, planetary dynamics.
I guess when Atta leaves this time, we gotta get out of here now, and I mean it.
Atta has turned into a pumpkin,
Bye bye,
and
Atta. Have
yep,
a good night.
have a great one. And I think I'm going to do exactly the same. I don't think I'm going to turn into a pumpkin though tonight. I'm going to turn into something else. I don't know what yet. I haven't decided. So
well, keep your thoughts and prayers with our friend Bill for the Treville. He went to the hospital today.
Oh,
for some observation stuff. We don't know what's wrong.
oh wow. So
No clue.
he's not feeling well, I suppose.
Apparently not. Don't really know what's up. Don't know the whole story yet, but just keep your thoughts and prayers with him. And for anyone who knows him, Bobby knows who he is. You know, so
Absolutely.
just keep your thoughts there.
Good.
All right.
Yeah.
We will do it. All right. I am going to get out of here for now. Make sure to check out my Patreon page. Just look for Cosmic Lettuce. I'm doing some pretty interesting research, and I want to do it as full time as I possibly can. So
all right.
Look and see if you can support that a little bit. I'm going to publish, the whole thing. It's just like, doing real science. In fact, it is doing real science. So, all right, everybody, I'm going to get out of here for now. Peace, cheers, and all of those great things. Have a great evening, a great day.
And prosper, and trolls can just suck it.
All right.
Trolls just, just sort of slip on by. We will acknowledge your existence, and
tell a friend.
You can move on. Tell a friend, and subscribe if you haven't already. Thumbs up, and that's it for now. I'll be back here again tomorrow, 2 hours UTC. More astronomy, more space, science, nerdy things, who knows what. More math mistakes, probably. So almost guaranteed. So, okay, everybody. I'll see you later. Bye.
Bye.
Later.